All right, everybody, welcome back. We are now headed into lesson 4. This is going to be our Remix FundMe. And once again, you can find all the code associated with this lesson in the GitHub repository associated with this course, and also web3dev.education. And let's do a quick walkthrough of these contracts before we actually start coding anything to see what we're going to be doing. We're going to be creating one contract, fundme.sol. We're also going to have another file called priceconverter.sol, and we'll talk about that in a little bit. The fundme contract is going to be our main contract. This is going to be an example of a crowdsourcing application or a way to raise money. You can think of it as a Web3 decentralized Kickstarter. We'll allow users to send Ethereum, Polygon, Avalanche, etc., or really any native blockchain cryptocurrency into this contract and allow the owner of the contract to actually withdraw all the funds for them to go spend on their new project. And we are going to actually deploy this contract to a testnet. And remember, use the testnet transactions sparingly. But if we deploy this to a testnet, we scroll down, we actually see that we have a couple of buttons and a new color button. We'll actually get a new red button for our fund function. A red button indicates that a function is payable, and we can send native Ethereum or Polygon or Avalanche or whatever the native cryptocurrency of the blockchain we're working with is. We additionally will indicate a minimum USD amount to send to the contract. So funders have to spend at least $5 worth of Ethereum in order to call this fund contract. So if we go up to the value section, we can actually send some value with this transaction. And again, don't worry about this making sense yet. But if I want to send 0.01 Ether, I'll grab that amount in Way, paste it into the value section here. I'll scroll down, I'll hit the fund button. MetaMask will pop up. I'll confirm. We can see at the top, the current balance of the contract is 0. And we'll wait a little bit for the transaction to finish going through. And after the transaction finishes going through, we can see in Etherscan, we have a balance of 0.01 ETH. And we can also see that after remix, after a slight delay. Then we can allow the owner of the contract to withdraw those funds. Right now, the owner of the contract is also us. And after this transaction goes through, we'll see that balance removed from the contract and it'll go back into our wallet. And as you just saw there, if we held our MetaMask up for long enough, eventually it would pop back into our MetaMask. Are you excited? Well, you should be. Because after you complete this section, you'll actually know most of the fundamentals of working with Solidity. We're going to be going over a lot of advanced features in this section, and I'll let you know the specific parts that you don't need to fully understand quite yet. There's going to be a couple parts where if it doesn't totally make sense, just keep going with the course, and as we get later into the course, you'll figure out why they make sense. But it might be a good idea to write down the questions that you have to ask either an AI on the GitHub discussions or web3education.dev. Make sure, of course, to use the discussions tab in the Foundry full course F23 to ask questions and interact with other developers who are taking the same course. Or go to web3dev.education to learn more. All right, let's get froggy. So the first thing that we want to do is let's once again delete everything in our remix so we can start from scratch. So I have the contracts that we're actually going to be building in here. You might have the simple storage, the add 5 extra, the storage factory, etc. Let's go ahead, right click and just delete everything. We're going to start completely from blank here. So let's go ahead and delete everything in here. All right, great. So let's go ahead and start creating our contract. We're going to call it fundme.sol. One thing that's really good when you actually start building any code at all is to first write down what you want it to do. So what do we want ours to do? We want to get funds from users into this contract, withdraw funds to the owner of the contract or whoever has created this fundme contract. And then we also want to set a minimum funding value in USD. We don't want people to be able to donate just a penny. So let's go ahead and set this up. SPDX, license, identifier, MIT, do pragma, solidity, caret, 0.8.18, contract, fundme. Let's go ahead and delete these comments. So before we embark on writing all of our functionality out, let's just write down the functions that we want to build. So we're probably going to want a function fund, which is going to be the function they call to send money to our contract. We're going to want a function withdraw, which is going to be the function that the owner of the contract is going to use to withdraw the money that the funders send us. And those are going to be the two main functions that our contract is going to need. We're going to be implementing more functions than just this, but these are going to be the main functions to interact with our protocol or interact with our fundme contract. Let's comment out withdraw for now and just start focusing on fund. We want anyone to be able to call this fund function. So we're going to make this public. And we want this function to do what? Well, we want it to allow users to send money, and we want to have a minimum dollar amount that they have to send. So the first question we need to answer is, how do we send ETH to this contract? How do we have it when a user calls the fund function, ETH automatically gets sent into our contract? Whenever we send a transaction on the blockchain, there's actually always a value field that gets populated. And most of the time it gets sent with 0. Even before, when we called the send function between our accounts, when we added an amount in our MetaMask, this amount value populated the value field of our transaction. This value field is the amount of native blockchain cryptocurrency that gets sent with every transaction. The first thing that we need to do to allow a function in Solidity to accept this native blockchain currency in the first place is to make the function payable. It's this payable keyword that makes the function look red in the Remix UI. Just like how wallets can hold funds, contracts can actually hold funds as well. So whenever you deploy a contract similar to a wallet address, it actually acts almost the same as a wallet address. You can send money to it, you can interact with it, etc. And like we did in the demo, you'll see this contract actually gain a balance, just like a wallet. You can access this value amount of a transaction using one of the globals in Solidity called message.value. Solidity has a number of these globally available keywords and functions, and you can find these in the Solidity documentation. One of them is message.value, which is the number of way sent with the message. If we wanted users to be required to spend at least one whole Ether with this fund function, we could use something called require to do so. In order to do that, we would add this line, require message.value is greater than 1 E18. And there's a couple of things to unpack here. 1 E18 is equal to 1 Ether, which is equal to 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8. Or put another way, it's equal to 1 times 10 raised to the 18th. In Solidity, a double asterisk or double multiply sign is how you do a power or an exponent. This value here is the value in way of 1 Ethereum. In your smart contracts and at the lowest level, this is how they process numbers in this giant way format. So if we wanted people to be forced to send at least one whole ETH with this fund function, we would just say require message.value is greater than 1 E18. You can use something like ethconverter.com to see to convert 1 Ether between Ether, Way, and Gwei is actually another value in between Ether and Way. And we saw Gwei actually when we saw gas costs. Normally gas costs are shown in forms of Gwei. This required keyword is a checker. It's basically saying, hey, is message.value greater than 1 E18? If not, then revert this transaction. And if we want, we could add a little revert message. We could say like, didn't send enough ETH. We can actually deploy this. We can actually compile and deploy this on a Remix VM. Deploy, scroll down, and if we hit fund, and if we pull up our terminal, and we hit fund, we actually see we get this little X here, meaning our transaction didn't go through. And if we hit the dropdown, well, again, same thing. We know that this error is because we have this require statement in here, and our transaction is reverting or not going through. So we know that with this transaction, we need to send at least 1 ETH or 1 E18 way worth of ETH in the value section of our transaction. So if we scroll up, we can actually just change the unit to Ether, put 1 in here, scroll down, and now if we hit fund, oh, it doesn't go through because we have strictly greater than. So excuse me, let's do 2. Now we'll scroll down, we'll hit fund, and we get a green check mark, and we see the fund me balance actually has improved to 2. If we update the value to 2 again, and we scroll down, we hit fund again, we see our transaction went through, and we have 4. If we try to do less, like let's change this to way, and we'll do 1,000 way. Scroll down, we hit fund, up, it fails because 100 way is less than 1 E18 way, right? Because 1 E18 way is this much way. So obviously 1,000 or however much I put in is much less. So this require says, if this first section is false, then go ahead and revert with whatever this second section is. Reverts can be a little bit confusing and a little bit tricky. So what is a revert? A revert undoes any actions that have been done previously and sends the remaining gas associated with that transaction back. So what does that actually mean? Well, let's say, for example, in our FundMe contract, we have a uint256 public my value, and let's have my value initialized to 1. Now in our fund function, let's say my value equals my value plus 2. So every time this fund function successfully goes through, we add 2 to my value. However, if we get to a revert statement, even though we added 2 to my value previously, since our contract reverts, this would actually revert this action or reset it back to its initial state. So if this transaction reverts, my value would go back to 1 or whatever it was previously. If we compile FundMe, we delete our previous deploys. We're on the Remix VM. We'll deploy FundMe. We'll scroll down. We have my value, which defaults to 1. If we call fund right now without any value, If we pull up our terminal, we can see the transaction failed. My value is still 1, even though this line technically executed. This line executed, but then this line hit and it reverted what was done here. So if we scroll back up though, we go to Ether, we'll put 1 in for now, scroll back down. Now we'll hit fund. Oh, needs to be more than 1, excuse me. We'll add 2 here, scroll back down. Now we'll hit fund. That transaction did go through, which means my value will now be equal to 3. And again, if I set value to 0, we call fund, it reverts, so my value is still 3. So then the question might be, oh, well, did we spend gas to do this if my transaction didn't even go through? Well, unfortunately, the answer here is yes. If you send a failed transaction, you will spend gas because computers executed this line and then they executed this line and just failed. So users can actually specify how much gas they send with every function. Let's say there was a ton of computation after this require line, we would need to send a ton of gas to operate and run our fund function. However, once it gets to this require line and it reverts, however much gas that we sent to execute the rest of the computation would just get refunded to whoever initiated the transaction. Like I said, sometimes the refunds and some of that can be a little bit confusing. So again, for now, just know that if a transaction reverts, it undoes anything it does previously, and you can consider the transaction failed. However, if you send a reverted transaction, you will still spend gas. But okay, let's delete this value for now, delete it from the global scope, and delete some of these like that. In fact, every single transaction that we send will have these fields. It'll have a nonce, or the transaction count for the account, the gas price, the gas limit that we've seen on Etherscan, a to, aka the address that the transaction is sent to, a value, which is going to be this amount that we're talking about. We'll also have data, which is going to be what we send if we make a function call or deploy a contract. And then it'll have this VRS components. We're not really going to go over these VR and S because this is that cryptographic magic that's happening when a transaction is signed, but just know that that's in there. For sending value, we can populate some of these fields. The gas limit, for example, is populated to 21,000. Data is going to be empty. And then that 2 is going to be the address of the transaction we want to send to. For a function call, we can also still populate the way that we want to send. So we can call a function and send a value at the same time. In Remix, it has a little drop down here for way, gwei, fini, and ether. We're going to ignore fini for now, but of course we have our way, gwei, and ether again, where 1 ether is worth this much gwei and this much way. So right now our contract is pretty minimal, right? We're requiring the message.value is greater than 1 whole ether, but we want to actually require that it's less than some value. Like, let's say we want to have users spend a minimum of $5 as opposed to 1 whole Ethereum. So let's first specify that $5. We can do that at the top of our contract. We'll say uint 256 minimum USD equals 5. And we'll make this public instead of internal. We'll update this minimum USD in the future to make this more gas efficient. So what we want to do is we want to require that our fund function requires that the message.value is greater than, let's say greater than or equal to minimum USD. However, minimum USD is in terms of USD or dollars, and message.value is in terms of ETH or way in terms of Ethereum. So how do we convert the amount of Ethereum to its price in dollars? This is where oracles and Chainlink comes into play. The dollar price of an asset like Ethereum is something that we've assigned to Ethereum outside of the blockchain in the real world. So in order to get this abstract concept of the price of the native cryptocurrency of the blockchain we're working with, so we need to use a decentralized oracle network or something called an oracle to get this price. So before we keep going, let's learn a little bit more about decentralized oracles, Chainlink, and how they work so that we can understand how to get the price of Ethereum into our smart contracts. As we've talked about, blockchains are deterministic systems, which means that they themselves can't actually interact with real-world data and events. They don't know what the value of an Ethereum is. They don't know what random numbers are. They don't know if it's sunny outside. They don't know the temperature. They don't know who's president. They don't know any of this information. These blockchains also can't do any external computation. Maybe you have some amazing artificial intelligence model that you want to integrate with a smart contract. Smart contracts by themselves can't do anything with that. As we've mentioned, this is because blockchains are deterministic by design. This is so that all the nodes can reach consensus. If you start adding variable data or random data or values that return from an API call, different nodes could get different results and they would never be able to reach a consensus. This is known as the smart contract connectivity problem or the Oracle problem. And this is bad news because we want our smart contracts to be able to replace traditional agreements. And traditional agreements need data and they need to interact with the real world. So this is where Chainlink and blockchain oracles come into place. A blockchain oracle is going to be any device that interacts with the off-chain world to provide external data or computation to smart contracts. However, the whole story doesn't even end there. If we use a centralized oracle, we are reintroducing a point of failure. We've done all this work to make our logic layer decentralized, but if we get our data through a centralized node or through a centralized API, or we decide we want to make the API call ourselves, we are reintroducing these trust assumptions that we've worked so hard to get rid of. We're essentially ruining the entire purpose of building a smart contract. So we don't want to get our data or do external computation through centralized nodes. Those are bad news. Chainlink is the solution here. Chainlink is a decentralized oracle network for bringing data and external computation into our smart contracts. As we mentioned before, this gives rise to these hybrid smart contracts, which combine on-chain and off-chain to make incredibly feature-rich, powerful applications. Chainlink is a modular, decentralized oracle network that can be customized to deliver any data or do any external computation that you like. So, for example, a lot of people say, oh, I can just make an HTTPS call to some API and we'll be good to go. The blockchain nodes can't make these HTTPS calls because they wouldn't be able to reach consensus. If they called the node at different times or they did something else, all the consensus would be broken. So instead, we need a decentralized network of Chainlink oracles to do this. And then in the transaction, this network of nodes will return the data to our smart contracts for us. Now, Chainlink networks can be completely customized to bring any data or any external computation that you want. However, doing the customization can be a little bit extra work. There are a ton of Chainlink features that come out of the box completely decentralized, ready to plug and play into your smart contract applications. What are those features? The first one is going to be Chainlink data feeds, and that's the one we're actually going to be using for our application here. Chainlink data feeds, currently at the time of recording, are powering over $50 billion in the DeFi world. The way they work is a network of Chainlink nodes gets data from different exchanges and data providers and brings that data through a network of decentralized Chainlink nodes. The Chainlink nodes use a median to figure out what the actual price of the asset is, and then deliver that in a single transaction to what's called a reference contract, a price feed contract, or a data contract on chain that other smart contracts can use. And then those smart contracts use that pricing information to power their DeFi application. We can see an example at data.chain.link. And you can change networks, you can change price feeds, you can change a whole bunch of different information to see some of the most popular price feeds. Let's look at ETHUSD, for example. On ETHUSD, we can see this whole network of independent Chainlink node operators that are each getting different answers for the price of ETHUSD. They're getting aggregated by the network and then delivered on chain. We can see how often they're updated. These ones are updated for a 0.5 deviation threshold or a few hour heartbeat, whichever one hits first. We can see when the last update was, we can see the number of Oracle responses, etc. We can see the contract address directly on chain. We can even look at the contract on Etherscan. We can see some of the history. We can see all the responses of the different oracles. And then at the bottom, we can see the different users and sponsors keeping this network up. Similar to transaction gas, whenever a node operator delivers data to a smart contract, the Chainlink node operators are paid a little bit of Oracle gas in the Chainlink token. Right now, these users of the protocol are sponsoring keeping these feeds up and are paying the Oracle gas associated with delivering this data on chain. Here's an illustration of what the current model of these data feeds look like. A network of these Chainlink nodes each reaches out and gets the information about an asset and then signs the data with their own private key. In a single transaction then, one node will deliver all the data with all the different signatures to a reference contract. If that node doesn't deliver the data, another node will send it instead. Reputation is incredibly important when you're a Chainlink node operator. If you miss data updates, if you forget to send transactions, you'll probably be quickly kicked off these networks and have no chance of making any more money in the future. These data feeds are used by some of the largest protocols in the space, such as Synthetics, SushiSwap, Compound, and Aave. with several billion dollars each. We can take a look at an example over at docs.chain.link. Work with EVM contracts. We're going to hit EVM chains, scroll down to data feeds. We'll scroll down to the Solidity section, and we can see an example of an entire contract that uses and reads from one of these Chainlink price feeds. We can even open this up in Remix and work with it in Remix. It looks like this example is reading from a price feed on Kovan. The reason we're actually going to use a testnet to see this work is that there's a set of Chainlink nodes monitoring the test network to show you exactly how this works out. Once we get deeper into the course, we'll show you how to actually run tests and work with Chainlink nodes without actually being on a testnet, which will make your development much faster. But I highly recommend walking through this section along with me so that you can see firsthand how this actually works. So let's go ahead to faucets.chain.link/Kovan. We're going to switch to the Kovan network, and we're going to get some Kovan ETH. But remember, look at the network flag and use whatever network is in the documentation. So to get some Kovan, we're going to come to the faucet. We're going to turn off test link. We'll just stay with ETH. I'm not a robot. And then send request. Once our Kovan Ethereum has reached our wallet, we can go ahead and close. And we can take a look in our wallet and see that we do indeed have 0.1 ETH on Kovan. Now let's go back to our remix. We'll compile this contract. We'll go and deploy this on Injected Web3. And again, the reason we're going to use Injected Web3 instead of JavaScript VM is that there's no network of Chainlink nodes watching our little fake JavaScript VM. There are a network of Chainlink nodes watching the testnet. So we'll scroll down. We'll switch contract to the price consumer v3, and we'll hit deploy. MetaMask will pop up, and after a brief delay, we can see our price feed consumer down here, and we can hit get the latest price, which shows us the latest price of Ethereum in terms of USD. You may be wondering why the number looks so weird. That seems like a really large number for the price of Ethereum in terms of USD. And this is because decimals don't actually work so well in Solidity. And we'll get to that in a little bit. There's a decimals flag associated with this price feed address that tells us how many decimals to include with this price. It's also in the documentation. However, I know that this one has 8 decimals. So this is saying the value of Ethereum right now is $3,262. It may, of course, be different when you go ahead and try this. Now, there's a number of things that happen in this contract that I'll explain in our FundMe example. But if you want to take a look now and see if you can figure out what's going on, I recommend you do so. Price feeds are one of the most powerful out-of-the-box decentralized features you can use in your smart contract to level them up, especially for decentralized finance. If you're looking for different addresses of different price feeds, you can check the contract addresses section of the documentation, choose the network that you want, and then scroll down and then look some of the different addresses of the different price feeds. For example, this address will give you the price of 1-inch token in terms of Ethereum. This address will give you the price of the Apple stock in terms of USD, and so on and so forth. The next decentralized application right out of the box is going to be Chainlink VRF, or Chainlink Verifiable Randomness Function. Once we do our lottery example a little bit later, we'll talk about how randomness can be manipulated in blockchain. Blockchains are deterministic systems, which by definition means that they can't have randomness. If you can determine what a random number is, it's not really random anymore, is it? So we need a way to get a provably random number by looking outside of the blockchain. And oracles are perfectly positioned to do exactly that. Chainlink Verifiable Randomness Function is a way to get provably a random number into our smart contract to guarantee fairness and guarantee randomness of applications. Many protocols like Pool Together, Axie Infinity, Ether Cards, Avagochis, and more use Chainlink VRF for lotteries, for randomizing NFTs, for gaming, and for more. We're going to do an example of Chainlink VRF in a later section once we get to the lottery section. If you want to see if you can play with the randomness yourself right now, I recommend you going to docs.chain.link, EVM chains, and scroll down to get a random number. And this will teach you how to get a provably random number into your applications. The next decentralized out-of-the-box feature of Chainlink is Chainlink Keepers, which is decentralized event-driven execution. As you've seen, in order to kick off some type of transaction, somebody needs to spend the gas and somebody needs to sit down and hit the go button or hit the transact button or hit the send button. This is obviously a centralized vector if you have a decentralized application that needs to run at specific times or after specific events are triggered. Chainlink keepers are the solution to this. Chainlink keepers are Chainlink nodes that listen to a registration contract for different events that you specify to fire. Maybe you say every 10 minutes you want to do something, or once a week do something, or if the price of some asset hits some number, or maybe a liquidity pool is at a certain level. Whatever event that you want to code, you absolutely can. The Chainlink nodes constantly listen for these triggers to happen and check the different contracts for these triggers. Once a trigger returns true, the Chainlink nodes will then perform whatever action that you tell the Chainlink nodes to do. We're also not going to go over the Chainlink keepers examples right now because we're going to get to them in a later module. However, if you want to try them out, go to docs.chain.link/Ethereum, go to making compatible contracts, and feel free to read the documentation and try it out yourself. The last out-of-the-box feature of Chainlink is the most customizable, but also the hardest to get correct. End-to-end reliability is the ultimate promise of our smart contracts, and we want and need them to be able to do anything. We want to be able to take any input and get any output. Chainlink Functions is the last decentralized out-of-the-box tool, and it allows you to make any API call in a decentralized context through a network of Chainlink nodes. We're not going to be going over that at all in this video, but be sure to check out the documentation if that's something that you're interested in. To me, Chainlink Functions is going to be the future of DeFi and smart contracts. And if you're looking to make something novel, and if you're looking to make something that's never been done before, I 100% recommend you check out Chainlink Functions later on after this course or whatever you want to do. As of filming, it came out about a month or two ago, and people are just beginning to build amazing things with Chainlink Functions. So be sure to check this out after or during the course. We're going to be using the Chainlink automation in a later section in this course. Again, if you want to try these out in Remix on a real testnet, you can go to the documentation and play with them here. Now, I know we haven't actually written that much code, but we've gone over a ton, so I want to do a quick review. In order for a function to receive native blockchain token like Ethereum, you need to mark that function as payable. If you want to force a transaction to do something and you want it to fail if that wasn't done, you can use a require statement. A transaction that reverts means it undoes any work that it did previously and returns any gas to the user. To get the value sent with a transaction, you can use the Solidity global message.value. Chainlink is a technology for getting external data and computation into our smart contracts. And most importantly, getting that data in a decentralized context. In this example, we're going to be using a Chainlink data feed or a Chainlink price feed, which is a decentralized way to get pricing information from real-world assets into our smart contracts. Now, in order for us to figure out if the amount of Ethereum sent with a transaction is greater than or equal to our minimum USD of $5, we need to convert the amount of Ethereum into its value of dollars. So how are we going to do that? Well, the first thing that we're going to need to do is we're going to need to get the price of Ethereum or Avalanche or Polygon or whatever native blockchain token that we're working with. So let's create a function to do that. We'll create a function, get price, and this function is just going to get the price of Ethereum in terms of USD. And then we're also going to create a function called get conversion rate, which is going to convert a value to its converted value based off of the price. For now, we're going to make them both public functions so we can play with them, test them, and do whatever we want with them. To get the price of Ethereum, we're going to use a Chainlink data feed, and we can go to the documentation to get that information. So in the documentation, I'm going to scroll down using data feeds. They've got an example here, right in Solidity. And if you wanted to, like I said, you could easily open this up in Remix. Now you can see this example in the documentation, what's actually going on when we're working with a Chainlink price feed. There's a contract out there at an address, and we're going to call this latest round data function on that contract. It gives us a whole bunch of data, but we really only care about the price. So we're going to want to do the same thing. We want to reach out to that contract that's currently storing and having the price updated. So since we want to reach out to and work with the contract, we're going to need two things, right? What are those two things? Well, we need the address and we need the ABI. The address of the contract is going to be really easy. We can get the address by going to the Chainlink documentation, and let's go to this price feed addresses section. We'll scroll down. We want to be on Ethereum. Okay, great. Let's look for Sepolia. Looks like it's way down here. And all right, awesome. ETHUSD. Great. There's an ETHUSD price feed. So now that we have the address, how do we get the ABI? Well, before with simple storage, we imported the entire contract from the top and we compiled and we got the ABI like that. We could do that here, but that's kind of a lot of code. And we don't actually care about what the whole contract looks like. We only really want to know what the functions are, so we can call that latest round data function. Remember, if we're on Remix and we go down to the compilation details, The ABI is really just this list of functions that we can call on a contract. The ABI itself doesn't actually need to include any of the logic. It just needs to say, hey, these are the functions you can interact with, and here are their inputs, and here's whether or not they're payable, and here's whether or not they're view functions, etc. Like I said, though, this kind of is a white lie. You can also use a function selector or some other ways, but we're just going to ignore that for now. How can we get the ABI? There's a concept in Solidity known as the interface. If we go to the Chainlink GitHub, and we go to smart contract kit/Chainlink, we can see a lot of the different contracts in the Chainlink repository. We can go to contracts, SRC. This might look a little bit different based off of when you're looking at it. V0.8 interfaces, and we go to aggregator v3 interface. If we scroll down, we can actually see a whole bunch of function declarations, but none of them are actually implemented. It's just function, the name of the function, some stuff, external view, blah, 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 but then just the semicolon and nothing inside of them. This is what's known as an interface. If you compile this, this will actually give us that ABI because it defines all the different functions that you can call on a contract. It just doesn't have any of the logic. Again, we don't really even need to know what the functions do. We just need to know how to interact with the contract. And if a contract is deployed, it'll have that logic in its deployment. So what we can do is we can copy this whole thing, scroll all the way to the bottom, hit the copy button, and paste it in on our remix. Now, hold on though, if you're following along, you don't have to copy paste it in here with me because I'm going to teach you something in just a minute that makes this a little bit easier. This pasted code alert comes up. We're running Solidity code, so this is going to be okay. Since we're only working on testnets here, we're going to be okay that we don't have to worry about pasted code alert. If you want to take a second to read it, please do. But we're going to paste this code in here, just like we did before with simple storage. For now, you don't have to follow along. I'm about to show you an easier way. Just follow along and watch. Now that we have this interface, aggregator v3 interface, we can use this interface to make API calls because now we have the address and we have the ABI. And we can even compile this and it'll compile fine. So we can say aggregator v3 interface at address this, and the combination of these two give us whatever code is at this address with all the functions from the aggregator v3 interface. And just to test this out, we could do something simple like .version, since if we scroll up, it looks like there is indeed a version function. Put a little semicolon at the end. So let's actually go ahead and actually copy this line, give it its own function called getVersion. This will have this public view returns. What is the version up here return? A uint 256. We'll have a return a uint 256. Paste that line in here. Aggregator v3 interface at its address .version. We'll say return all of that. Now I'm going to go ahead and deploy this to the Sepolia testnet just to show you what this would actually look like. However, I'm going to recommend you don't do that for now. Just know that this will work. This way you won't have to wait forever for your transactions to go through on the testnet. So to do this, I'm going to go ahead, scroll up to the top, go to inject a MetaMask, change the contract from aggregator v3 interface to fundme. I'm going to go ahead and hit deploy. My MetaMask is going to pop up. I'm going to go ahead and hit confirm, and we're going to scroll down. And now we have a big blue button called get version, which I'm going to go ahead and click. And we can see we get a 4 return because at this contract address on the blockchain, it has the functionality for get version returning 4. And for the rest of this lesson, I'm going to be showing you guys and testing this on an actual testnet. However, I recommend that you don't test all of these as I go along. Just watch me do them because again, waiting for transactions on a testnet can be really annoying. Sometimes the testnet might be having issues because again, it's people running them out of the goodness of their heart. So for this lesson, just follow along, write the code with me, and then maybe at the end, deploy everything. So this is a really easy way and a common way that people use to interact with other contracts outside of their projects. They get the interface of that contract using the interface keyword. They compile it, and the compiler actually gives us an ABI. And then you just wrap an address around with that interface keyword, and you can call any function at that address. And this is one of these things, as we work with more and more, it'll start to make more sense. In the beginning, it might be a little hard to grasp, but just bear with me for now. The more we do it, the better you'll get. Don't get discouraged. Take a deep breath and exhale, and let's keep coding. And if this is confusing to you, this is again where we can work with our AI friends or any of the forums that we're working with. Again, very soon, I'm about to show you how to ask really good questions and make really good prompts. But one we could ask here is, hey, I'm confused. How does the Solidity function return the value 4 when I didn't define any logic in aggregator v3 interface? And I just posted that code from getVersion here because a common issue that I see new developers run into is they go, oh, wait, how does this version return 4? My aggregator v3 interface doesn't have any code in it. Why does putting an address in here make it work? Like what's going on? And let's see if our AI is able to help us here. So this is ChatGPT version 3.5. Again, I prefer version 4, but this is the cheaper one. And it says, in the code you provided, the get version function is calling the version function of an instance of the aggregator v3 interface contract. It appears that the contract address here is being used to create an instance of aggregator v3 interface. The aggregator v3 interface is an interface contract that defines a set of functions that must be implemented by another contract. It serves as a way to interact with the contract at the given address by providing a common interface. The version function being called in your code is likely defined in the actual contract that implements this. And this is pretty much correct, right? And so it gives us some more context here. This is exactly correct. This address has a version function, and us surrounding it with this aggregator v3 interface, like typecasting it in these parentheses like this, is just telling our Solidity compiler, hey, there's a version function at this address, or there's a latest round data function, or all the functions in this aggregator v3 interface are at this address. If this address doesn't have a version function, this would just break. And this is a good example of, again, where we can actually follow up with these AIs. They're typically very good at keeping context. So we could even ask, what would happen if that contract address didn't have that function? And we see if the implementation contract at the given address does not have a version function, or if it has a different function signature, calling version on the contract would result in a compilation error or a runtime error. So it wouldn't result in a compilation error, but the transaction would revert. So this is pretty helpful here. But again, we always want to double check this. So this is where we'd probably go back to the discussions forum and follow up there. So now that we actually have the interface, we can start calling these functions and calling these addresses. However, having a ton of these interfaces is really going to clog up our contracts and clog up our files and be really gross to work with. Is there a better way for us to do this? Well, when we worked with simple storage, yes, there was. We just went ahead and used imports, right? But that's when we had all the code locally in our directory. We don't have all the code locally. We didn't create the aggregator v3 interface. We didn't create the price feed contracts. So can we do something like import simplestorage.sol, but with a contract outside of our project? Well, again, we could copy paste it to its own file and import aggregator v3 interface.sol. And of course, we're going to use this named import syntax because we're awesome developers. We could copy paste it like this and do exactly what we did before. We could create a new file called aggregator v3 interface, paste the code in there, or we could actually import directly from GitHub. If we go back to the documentation associated with using data feeds, we scroll down to using data feeds here, scroll down, we see at the top, they do this import like this, import at chainlink/contracts, src, blah, blah, blah. This import actually has the same setup as the path of what's in the GitHub repository. So instead of us copy pasting from GitHub, we can actually import directly from GitHub or NPM. We can copy this line back in our remix. We could paste it in like this. Remix is smart enough to know that this at chainlink/contracts is referring to what's known as an NPM package at chainlink/contracts. At chainlink/contracts is what's known as a package manager, and it keeps different versions of combinations of code for us to download. At chainlink/contracts is created directly from Chainlink repository. Remix downloads all this code from NPM, which is created from the GitHub. So it essentially downloads it from the GitHub. So us doing this import like this is the same as just copy pasting the entire interface at the top of our contract. And now we have this aggregator v3 interface that we want to work with. We can go ahead and compile, and bada bing, bada boom. So great. So now that we have the interface here, which will give a minimalistic ABI for us to interact with the contract, how do we actually get the pricing information? Well, again, if we go back to the docs, we can see right here, it gives us an example of the code we can use to get the latest price. But let's write it ourselves just so that we know what's going on. We'll say aggregator v3 interface, and we'll actually create a new variable called price feed equals aggregator v3 interface contract at this address, which again only works for Sepolia. Now we can call this latest round data function on the price feed. So we'll say price feed dot late round data. And if we look at the interface on GitHub, we can actually see latest round data doesn't just return one variable, it returns a whole bunch of different types of variables. And to return multiple types, we do some syntax that looks like this. And we'll say uint 80 round ID. And you can even flip back and forth between the documentation, make sure you have it right. Int price, which again, we know an int defaults to an int 256. Uint 256 started at. uint 256 timestamp, and then uint 80 answered in round. Oh, there's a lot of code in here. Since this function returns so many variables, we have to set something up to capture them. But we don't care about any of this other stuff. We just care about price. So what we can do is actually just remove them and leave the commas in there. So we're going to remove started at, remove timestamp, remove answered in round, and I hit Command S to compile. We're going to get these yellow squiggly lines, which are warnings, but we're going to fix them in a minute. Now we have int price equals pricefeed.latest round data because we only care about getting the price from the return. The reason price is an int 256 is because some price feeds could be negative. Now that we have the price, this price variable is going to be representing the price of ETH in terms of USD. And it's going to return a number that looks like this because, again, Solidity doesn't work with decimals. So we know that this price feed has 8 decimals, but it'll get a return like this. Boom, like this. It'll return a value that looks like this. If we want to double check how many decimals there are in a price feed, it actually has a decimals function, which allows you to check that as well. Now, as we know, message.value is going to have 18 decimal places. How do we know that? Well, because we know that 1 ether is equal to this many way, and this many way has 18 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So this massive number is equal to 1 Ethereum, right? 1.12345678910 1234567 So right now, message.value and price actually have different decimal places. Price has 8. Message.value is going to have 18. So to get them to match up, we have to do return price times 1e10, or to add those additional 10 decimal places. And yes, I know we have a red line. I'll fix this in a minute. Price, as we know, is a int 256, and message.value is going to be a uint 256. So the types are actually different. So we want to get the price in terms of uint 256 instead of int 256. To convert them, we can again do a thing called typecasting. There are a lot of different types that can be easily converted between each other. Not all types can be typecasted, but an int and a uint 256 can be. So to make our price a uint 256, we would just do uint 256 and wrap price like this. Or we could just wrap both of them like this. Now, of course, since we're not modifying any state, but we are reading storage, we can make this a view function, and then we'll say it returns a uint 256, like so. And now, if we compile, we get rid of all those errors and warnings. Now, math can be a little bit tricky in Solidity, but the more you do it, the better you'll get. And the reason math can be tricky is because there aren't any decimal places, so you need to only work with whole numbers. The more you work with it, the better you'll get, though. Awesome. So now we have a getPrice function, which is going to return the value of Ethereum in terms of USD as a uint 256. Now, all we have to do is convert our message.value in terms of dollars using this getPrice function. To do that, we're going to use our getConversionRate function. This getConversionRate function is going to take a uint 256 ETH amount as an input, and we're going to convert this ETH amount to its value in dollars. This will be a public view function that will return a uint 256. So first, we're going to get the price of Ethereum by doing uint 256 ETH price equals our getPrice function that we just defined. And then we're going to do uint 256 ETH amount in USD equals ETH price times ETH amount. And then we actually have to divide by 1e18. The reason we divide by 1e18 is because both of these have 18 decimal places. And if we multiply 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we multiply these by each other, where both of these are representing 1, we're actually going to get a number that's absolutely massive with 38 decimal places. So we need to divide by 1e18 to reduce it back down to what it should actually be. An important rule with working with math in Solidity is you always want to multiply before you divide. The reason for this is since, again, only whole numbers work in Solidity, if you were to do 1 divided by 2, you would end up getting 0. So you always want to multiply first. When we get to the Foundry section of this course, testing all this math is going to be a lot easier. If you're really struggling with some of the math bits right now, I wouldn't let that slow you down because one of the things that AI is really good at is doing a lot of these math conversions. But in any case, this ETH amount in USD is the number that we're looking for. So we can say return ETH amount in USD. And awesome, now we have a getConversionRate function. Let's walk through this together just so that you can understand what's actually going on. Let's say we want to see how much 1 ETH is worth. Well, we're going to get the ETH price, which let's say it's $2,000, but it's going to be $2,000 with 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 18 zeros. So ETH price might look something like this. So that means we're going to do this 2000 with 18 decimal places times 1 ETH, which is going to be 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10. We're going to multiply those together. And then since we're going to get an additional 36 zeros, then we just divide by 1 E18. And that's how we would get $2,000 equals 1 ETH. It's going to be 2,000, of course, with 18 decimal places. One of the good reasons for using whole numbers in Solidity is that it's not possible to have decimal places. So we don't lose any precision, which is really good. So normally we should test this function before continuing, but since we're doing all this on a testnet, and I promise you that I tested this all beforehand, we're just going to go ahead and keep going. So now that we've done all this work, if we want to make sure that our users are sending at least $5, we can do get conversion rate of message.sender needs to be greater than minimum USD, because get conversion rate takes an ETH amount as input, uses the pricing information to get the dollar value back, and we're going to check to see that the dollar value of the message.value is greater than the minimum USD. However, since get conversion rate returns a value with 18 decimal places, we need to update our minimum USD to say 5 times 10 raised to the 18th. Or we could also do 5E18, or we could do 5 times 1E18. I personally like this 5E18 syntax, but whatever works for you. I'm going to deploy this to a testnet just to demonstrate this working, but again, you do not have to. So we're going to go ahead, delete our previous deployments, injected Web3, deploy, MetaMask pops up. I'm going to go ahead and confirm. After a long delay, we'll get our deployed contract here. We have all this stuff. We can call get price, and we can see the value of Ethereum right now is this with 18 decimal places, which is awesome. So it's around $1,896. So if I were to try to fund this with maybe 100 way, I know for a fact that 100 way isn't going to be enough. So if we call this fund function, we're actually going to get this gas estimation failed. Gas estimation error failed with the following message, blah, blah, blah. Error, execution reverted, didn't send enough ETH, which is actually exactly the error message that we have here. It's exactly what our error message is here in our require, didn't send enough ETH. So if we try to fund it, we're going to get didn't send enough ETH. And this gas estimation failed is a pretty common error that you'll see in Remix and Solidity and EVM in general. It's kind of just the boilerplate answer for something went wrong. Luckily, we got the actual error message here so that we could debug, here's what's actually going on. Now you see here, we could still send this transaction. Like I said, we would actually spend gas to send a failed transaction. And this isn't something that we want to do, so we're going to go ahead and cancel. However, if we did send maybe 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we go to Google, actually, we can even see like an ETH to dollar conversion rate. So if we send 0.01 ETH right now is worth $18. It might be different depending on when you actually do it. So we send 0.01 ETH in our remix, and we can do that by doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6. So that's 1E16. And we hit fund now. We actually see MetaMask pops up. We don't get that gas estimation error. We can go ahead and confirm, and we can see that our function is working as expected, which is great. It's reverting transactions that have less than $5, and it's letting transactions go through that have at least $5. Awesome. And if we select minimum USD, we can obviously see that here. And we can see we have 0.01 ETH here. Fantastic. And since we don't have a withdrawal function here, we actually can't pull it out, which is another reason why I say, hey, maybe don't test this right now. But great, we've confirmed our get conversion rate is working. So let's move on. Fantastic. So what's the next thing that we should do in this contract? Well, we probably want to keep track of the users who send us money in this contract. So we can keep an array of addresses called funders and keep updating that depending on who actually sends us money. So up at the top, we'll make an address array or an address list. We'll make it public and we'll call it funders. And anytime somebody sends us money, we'll say funders dot push message dot sender. Like message dot value, message dot sender is another global variable we can use in Solidity, which refers to whoever called this function, the sender of the transaction to this contract. So if we're on Sepolia and we initialize a transaction from our MetaMask, the message.sender is going to be this account right here. And then maybe we want to even make a mapping of addresses to make it easier to look up how much money each funder has sent. So we'll make a mapping of an address to a UNT256. We'll call it public address to amount funded. Now, something that's newer in Solidity is you can actually name the types in your mapping. So you could say address funder mapped to UN256 amount funded. Usually this is what's known as a little syntactic sugar. It's just to make it easier to read what this mapping is, right? Funder to amount funded. And then our variable name is very explicit, address to amount funded. Now, if somebody funds our contract, we'll of course do address to amount funded, the message.sender's address plus equals whatever they previously have funded plus message.value, whatever they're additionally adding. All right, great. And now we have a way for us to keep track of funders sending money to our contract and have an easy way with a mapping to look up how much they've spent in total. Now, I know we've gone over a lot of advanced Solidity here, so let's do a quick refresher of what we've learned so far. Whenever we interact with a contract, we always need the address and the ABI. Compiling an interface allows us to get that ABI very easily for us to interact with another contract. When we combine the contract address with the interface, we can easily call the functions on that contract. Chainlink price feeds are an easy way to get data, especially pricing data, from the real world into our smart contracts. When working with math in Solidity and the EVM in general, decimals don't work. So we need to always make sure we're using the correct number of units whenever we interact with our contracts. Message.value and message.sender are known as globally available units in Solidity, and they refer to the sender of a message of the current call or the number of ways sent with a message or transaction. There's a whole bunch of these, and you can view them all in the Solidity documentation. All right, great. So we've got a way to actually get this pricing information pretty easily. However, our code is getting a little bit cluttered with these get price and get conversion rate. You'd think that these are functions that would be reused pretty often anyways for anybody looking to work with Chainlink price feeds. So is there an easier way for us to work with this pricing information? Maybe doing some math like this is pretty common, and we'd want other contracts to be able to import this conversion functionality. And a way that we can do that is actually creating something called a library. There's a site out there called Solidity by Example, which has great examples of using libraries and what they work with. Libraries are similar to contracts, but you can't declare any state variables and you can't send ether. A library is embedded into the contract if all library functions are internal. Otherwise, the library must be deployed and then linked before the contract is deployed. That's a little bit confusing. Don't worry too much about that right now. Using libraries can actually add functionality to different values. And what do I mean by that? Well, I mean, we can have our get conversion rate function be a function of any value of type UN256. Means we could take this get conversion rate and do something like message.value.get conversion rate. So we can create our own custom function with any type. So we could work with get conversion rate as if message.value was a class or an object or a contract that we actually created. To do this, let's go back to our files, create a new one called price converter.sol. And this is going to be a library, a price converter library. So how do we create a library? And what is a library? Well, a library is going to be very similar to a contract. We're going to start, of course, with SPDX license identifier. We're going to do pragma solidity, and we'll give it a version of 0.8.18, the little caret. And instead of typing contract, we're actually going to type library for the name of the library. And we're going to call this library price converter. So libraries can't have any state variables, and all the functions have to be marked internal. So what we're going to do is we're going to go back to fundme.sol. I'll zoom out a little bit. We're going to grab get price, get conversion rate, and get version, delete them. Well, I hit copy first, go back to price converter, paste them in here, and work with them in here. Of course, we're going to need the aggregator v3 interface. So we're going to go back to our fundme. We're going to copy this named import from aggregator v3 interface, paste it in at the top here, hit Command S, and we're going to go ahead and compile this successfully. Fundme is no longer going to compile, but we're going to fix that in a little bit. Now, the first thing that we're going to need to do in here is make these all internal. So we're going to say internal like this. We're going to do internal get conversion rate and internal get version. Now that we have our price converter library, we can actually import it back in our fundme and attach it to a UN256. And let's actually delete this aggregator v3 interface line for now. And we'll do import price converter from /price converter.sol. And now to attach the functions in our price converter library to all UINT256s, we'll say using price converter for UINT256. Of course, if we compile our fundme, we're going to get an issue because it doesn't really know what get conversion rate is. So for now, let's actually just comment out this line. I'm going to remove these comments up here as well. So what we can do now, though, is we can do message.value.get conversion rate. Get conversion rate. And in your library, whenever you're working with a library, The first input variable for a library is going to be the type that you're using with the library. So message.value is of type uint256. So this gets passed inside of getConversionRate as the first variable into uint256 eth_amount, even though we don't pass any variables inside of these parentheses here. For getPrice and getVersion, we don't really care to have an input parameter at all. So it'll pass it in, but not do anything. So now, instead of require getConversionRate of message.value, we can actually do, let's uncomment this line now, and let's delete this line. We can actually do message.value.getConversionRate. And now, if we compile this, this is going to compile successfully. This works because we're attaching the price converter library to all uint256s. So now all uint256s have access to this getConversionRate function. And since message.value is a uint256, it can call .getConversionRate and it'll pass itself, so that message.value, as the first input parameter to the function here. If we wanted another variable in here, like uint256 something else, that would be the first parameter inside these parentheses. So maybe like 123 or something, right? This 123 would be the something else, but message.value would still be the initial parameter, which in this example would be eth_amount. So let's go ahead and undo that and undo that. But all right, great. We've moved a lot of the math into our own library. Congratulations, nice work. One of the most common libraries that was used for a long time was this library called safemath.sol. And in your Solidity journeys, you'll probably see it pop up from time to time. Now, we're going to go off on a little bit of a tangent here about SafeMath and the library SafeMath. And this is an excerpt from my course last year, so you might see stuff like RinkB and some other stuff, but just focus on the SafeMath stuff. Just know when we refer to the JavaScript virtual machine, that's talking about the Remix virtual machine. One of the most common libraries that was used for the longest time was this library called safemath.sol. And you'll probably see it a lot of different places. We're going to go off on a quick little tangent here and teach you about SafeMath. So let's close FundMe and close Price Converter. And let's create a new file called safemath_tester.sol. And let's start with some basic stuff in here. SafeMath was all over the place before version 0.8 of Solidity, and now it's almost in no contracts. What happened? Why is SafeMath no longer used as much? Well, let's create a sample contract. This is a section that you don't have to follow along if you don't want to code along with me, but if you want to, you absolutely still can. This is going to be a contract we are going to deploy on a JavaScript virtual machine. We can use any version of Solidity before version 0.8 of Solidity. So for example, we'll use pragma caret 0.6.0, and we'll create contract safemath_tester.sol. Now, if I create a uint8 and I set it to public big number, and I set this to 255, oops, safemath_tester. Let's go ahead and compile safemath_tester with 0.6.7, pragma solidity. The maximum size of a uint8 is going to be 255. This is going to be the biggest number that we can fit in an uint8. And if I were to deploy this to a JavaScript VM or even a test network, safemath_tester, let's go ahead and deploy it. If I hit big number, we're going to get 255. Well, what happens if I create a function called add that sets big number equal to big number plus 1? Let's save that, delete that old contract, and deploy. Well, right now, big number is 255. What happens when we add 1 to big number, when 255 is the max size a uint8 can be? Well, let's hit add. And now let's check what big number is. Big number gets reset to 0. So what's going on? Well, prior to version 0.8 of Solidity, unsigned integers and integers ran on this concept of being unchecked, which means that if you passed the upper limit of a number, it would just wrap around and start back from the lowest number it could be. So if I call add a whole bunch more times and hit big number, now it's 8. If I were to hit this add button a ton more times and get it back to 255, it would then continue to wrap over to 0. So one of the most popular libraries that was out there was this SafeMath library, which would basically check to make sure that you weren't wrapping around a uint256 or an int256. Basically, it was a way to say, hey, you've reached the max this number can be, and now your transaction is going to fail. If we switch this to 0.8 of solidity, delete the old contract, we'll go switch this to 0.8. We'll go ahead and compile it. And now we deploy this to a JavaScript VM. If I hit big number, we get 255. But if we hit add, it actually fails and we still get 255. In version 0.8 of Solidity, they added this bit where it automatically checks to make sure if you're going to do what's called overflow or underflow on a variable. We can actually revert back to the unchecked version by using an unchecked keyword. So if we wrap this big number equals big number plus 1 in this unchecked bracket, let's delete our old contract, we'll compile, we'll redeploy. We hit big numbers, 255. Now we hit add, we hit big number again, it reverted back to 0. So that's a little bit more about safe math, checked and unchecked. So in version 0.76 and below, this code that you see in front of you is going to be the exact same as this code in 0.8 and above with this unchecked keyword. Now you might be thinking, in newer versions of Solidity, why would I use this unchecked keyword? Well, you'll find out later that this unchecked keyword makes your code a little bit more gas efficient. So if you're absolutely positive that your math is never going to reach the top or bottom limits of a number, then it might make sense for you to use the unchecked keyword. Let's head back over to our FundMe contract, where we are now using the price converter library that we just created. Awesome. We have a lot of the basics of the math that we need in our FundMe contract. So, all right, so this is great. People can actually send us money and we're going to keep track of them as well, which is fantastic. So the next thing, obviously, that we're going to want to do is we're going to want to be able to withdraw that money out. So now let's go ahead and implement our withdraw function. When we withdraw the money, we're probably going to want to reset all the mappings back down to 0 to show that, hey, we've withdrawn all the money and there's nobody left. To do this, we're going to use something called a for loop. A for loop is a way to loop through a list of something or to do something in a repeated amount of time. If you're familiar with other programming languages, it's the exact same concept. If we wanted to get all the elements in this list, for example, where 1 is at the 0th index, 2 is at the first index, 3 is at the second index, and 4 is at the third index, which I know is a little bit confusing. These are the indexes, and these are the elements. We would loop 0 through 3 to get all the elements out of this array. To do this loop, we're going to use the for keyword. We're going to say for, put some parentheses, and in a for loop, we can add a couple of things. And by the way, this is a way to do comments inside of a line in Solidity. You do a /*, */, and now everything in here is a comment. So in a for loop, you first need to give it the starting index, then you give it the ending index, and then you can give it the step amount. For example, let's say we want to start on the 0th index. We want to go all the way up to the 10th index, and we want to go by up each time. We would do 0, 1, 2, 3, 4, etc. Well, let's say we want to start with the 3rd index. We want to go to the 12th index, and we want to up by 2 every single time. Well, we would do 3, 5, 7, 9, etc. So our starting index is going to be a uint 256, and we'll call it funder index. And we're going to say we're going to start with 0. And we're going to end once the funder index is less than the funder's length. So I know I said up here, it's the ending index, but instead it's a Boolean. Once the funder's index is greater than funders.length, which is how you can get the length of an array, then we're going to end. And then finally, we're going to say every single time we do a loop, we're going to say funders index equals funders index plus 1. Now there's a shortcut you can do to do some variable equals itself plus 1, and that's just plus plus. This plus plus means every time we go through the loop, just add 1. And we actually don't need that here. And then we put these curly braces to say, okay, execute everything inside of this loop here for the duration that we specified here. And this final piece means that every time we run through all the code inside of these brackets, we're going to add 1 to this funder's index. That's how we go from 0 to 1, 2, 3, 4, 5, 6, 7, etc. To access the 0th element of our funders array, we're going to say funders of funder index. And this is going to return an address since it's an array of addresses. So we'll say address funder equals funders of funder index. And we want to use this to reset our mapping address to amount funded. So we can say address to amount funded at the funder address is now equal to 0. So we're going to reset whatever we added when they funded us down to 0 because we're withdrawing all the money out. And additionally, how there's a nice little shorthand like plus plus down here, up here in the fund, another nice little shortcut. Whenever you want to add something to something that already exists, instead of doing something equals itself plus the new thing, you can just do plus equals. This means that we're going to set address to amount funded of message.sender equal to itself plus message.value. So let's walk through this for loop a little bit. We're going to start with the 0th index. We're going to get the funder at the 0th index in our funder array. We're going to take that address, stick it into our mapping, and reset the amount that they've sent us to 0. Then we're going to do funder plus plus. We're going to check to see that funder index plus plus is less than funders.length. Obviously, fund 0 plus 1 is going to be 1. So we're going to check if 1 is less than the total amount of funders. And then we're going to get the address of the funder at the first index, reset them to 0, get the address at the second index, reset them to 0, third index, et cetera, until we finally reach the index that is equal to or greater than the length. So if we have 10 funders and we reach funder index 10, the for loop will exit and be done. But we still haven't done two things. We need to reset the array still, and then we also need to withdraw the funds, since we've accumulated all this message.value in the fund function. To reset the funders array, we could do the same thing we did with the mapping and reset each single address at each index, or we could just create a brand new funders array, which is what we're going to do. So to reset the array, we're now going to say funders equals new address array, and to start off at a length of 0. Previously, we used the new keyword to deploy a different contract. Now we're using the new keyword to reset the funders array to a brand new blank address array. This part's a little confusing. Don't let it hold you back. And later in the course, why we make the choices here that we do. So great. We've gone ahead and reset the array. So now how do we actually withdraw the funds? For this section, I'm going to go ahead and again refer to a previous course that I did because the content is exactly the same. Just remember, JavaScript VM is Remix VM. So great, we've gone ahead and reset the array, but how do we actually now withdraw funds from this contract? How do we send the funds back to whomever is calling this? Now, to actually send Ether or send native blockchain currency, there are actually 3 different ways to do this. We're going to look at all 3 and say what the differences between the 3 of them are. The 3 different ways are going to be transfer, send, and call. Let's go ahead and start with transfer, since transfer is the simplest and at surface level makes the most sense to use. So if we want to transfer the funds to whomever is calling this withdraw function, we would say message.sender.transfer, and then we'd get the balance of our contract here by saying address this keyword refers to this whole contract dot balance. And we can get the native blockchain currency or the Ethereum currency balance of this address like this, and we can just do that. Only thing that we need to do is we need to typecast message.sender from an address type to a payable address type. So message.sender is of type address, whereas payable message.sender is of type payable address. And in Solidity, in order to send the native blockchain token like Ethereum, you can only work with payable addresses to do that. So we just wrap it in this payable typecaster. So this is the first way that we can actually send Ethereum or send tokens from different contracts to each other. We wrap the address that we want to send it in this payable keyword. We do .transfer, and then we say exactly how much we want to transfer. But there are some issues with transfer. Here we are on Solidity by example for sending Ether, which again is a fantastic resource to refer to if you get lost. The method that we just looked at was this transfer method. Now, we saw way earlier in the course that if I sent Ethereum from one address to another, it cost about 2100 gas or 2100 gas. Our transfer function is capped at 2300 gas, and if more gas is used, it throws an error. The next one that we're using is going to be send, which is also capped at 2300 gas, and if it fails, it'll return a Boolean. So with transfer, if this line fails, it'll error and revert the transaction. With send, it won't error. It'll return a Boolean of whether or not it was successful. So using send, we'll do payable message.sender.send address this .balance. But we don't want to finish our call here. If this were to fail, the contract wouldn't revert the transaction and we just wouldn't get our money sent. So we want to do Boolean send success equals this whole bit here. And then we want to require send success. And if this send fails, we'll throw an error saying send failed. This way, if this fails, we will still revert by adding our require statement here. Transfer automatically reverts if the transfer fails. Send will only revert the transaction if we add this require statement here. So great. What's the third way that we can actually send Ethereum or native currency? Well, it's with this call command. Now, call is going to be one of the first lower level commands that we actually use in our Solidity code, because this call function is actually incredibly powerful, and we can use it to call virtually any function in all of Ethereum without even having to have the ABI. We'll learn the advanced ways to use this call much later. For now, we're just going to learn how to use it to send Ethereum or your native blockchain currency. Call is going to look very similar to send. We're going to do payable message.sender.call. And this is where we'll put any function information or any information about the function we want to call on some other contract. We actually don't want to call a function, so we're going to leave this blank. We can show that we're leaving it blank by just putting in these two quotes here. We instead want to use this like a transaction. And as we saw in our deployment, there's always this message.value bit. So we're going to use this call function as if it's a regular transaction, and we can add stuff like message.value. So in here, we're going to add these squiggly brackets, and we're going to say value address this dot balance. This call function returns actually two variables. And when a function returns two variables, we can show that by placing them into parentheses on the left-hand side. The two variables it returns are going to be a Boolean that we're going to call success, and also a bytes object called data returned. Since call allows us to actually call different functions, if that function returns some data or returns a value, we're going to save that in the data returned variable. It also returns call success, where if the function was successfully called, this will be true. If not, this will be false. And since bytes objects are arrays, data returns needs to be in memory. Now, for our code here, we're actually not calling a function, so we don't really care about data returned. So similar to what we saw with the price contract, we can just go ahead and delete that and leave the comma to tell Solidity, yeah, we know this function returns two variables, but we only care about one. And then similar to the send piece above, we're going to do require call success, call failed, meaning that we're requiring call success is true. Otherwise, we'll revert with an error that says call failed. Now, if learning the difference between these three is a little complicated for you right now, don't let that slow you down. Feel free to come back to this after you've learned more about how some of these lower level functions work and a little bit more about how gas works. Solidity by example does a fantastic job though of saying what the differences between all three are. Transfer has a maximum of 2300 gas and throws an error if it fails. Send has a maximum of 2300 gas, returns a Boolean if it fails. Call forwards all gas, so it doesn't have a capped gas, and similar to send, returns a Boolean if it is successful or if it fails. As of recording, right now, using call is the recommended way to actually send and receive Ethereum, or your blockchain native token. For now, if this part's a little bit confusing for you, for now, just look at this and see, that's how we send and transfer Ethereum or native blockchain currency tokens. And I'm going to delete this part for the video, but I'll keep those comments in the code repository associated with this course. All right, great. And actually the exact same code from that video, we're going to use for this as well. So we're going to use this call success to work with sending a balance. However, there's a bit of an issue here. Right now, anybody can call this withdraw function and take all the money out of this contract. We don't want that. We want anyone to be able to fund the contract, but we don't want anyone to be able to withdraw money from the contract. We only want the owner of the contract to be able to withdraw. So how do we set this contract up so that the withdraw function can only be called by the owner of this contract? Well, we want to set this contract up so that whenever we deploy it, whenever we create this contract, an owner gets assigned to this contract. We assign some address to being the owner, and then we add some parameters so that withdraw can only be called by that address. So what we could do is we could set up some function called call me right away. And when we deploy this contract, we would just immediately call this call me right away function, which will set us up as the owner. However, that would take 2 transactions. And remember, we're engineers. We want to work incredibly hard to be incredibly lazy. So instead, Solidity has something called a constructor. And if you're familiar with other programming languages, a constructor is the exact same as really every other programming language. And the constructor is a keyword and a special function in Solidity. So we can create a constructor function without the function keyword. We just call it structor. And we also don't even need the public keyword. You'll see Remix even highlights it pink. This is going to be that function. It's going to be a function that is immediately called whenever you deploy your contract. This function will be called in the exact same transaction that is used to deploy your contract. For example, if I were to take this minimum USD, add it in our constructor and say minimum USD equals 2, this minimum USD would immediately get updated to 2 right after this contract is deployed in that exact same transaction. Since we want this withdraw function to be able to be called by the owner of this contract, in our constructor, we can set up an address right away to be the owner of this contract. So let's create a global variable called address public owner. And then right in our constructor, we'll say owner equals message.sender. Message.sender, of course, being the sender of the caller, which in this example is going to be the deployer of the contract. Don't worry, we're going to demo all of this very soon to show you everything that's going on. If you want to test all this right now, absolutely go for it. But just remember, it's going to take you a little bit longer on a testnet, and I'm going to show you how it all works anyways. Now that we have our owner set up, we can actually modify our withdraw function so that only the owner can call this function. Easily enough, we're already familiar with the require keyword. We could add a require, the message.sender of whoever calls this withdraw function must be equal to, and this is how you do equals in Solidity with this double equal sign. A single equal is set, a double equals means equals. So message.sender must equal the owner. And if it's not the owner, we could revert with something like must be owner. Awesome. So now we have a quick way to require that whoever calls the withdraw function is indeed the owner. Awesome. But let's say we have a lot of admin functions or only owner functions or functions that should only be called by the owner. Would we have to put this line on every single function? Remember, we want to work incredibly hard to be incredibly lazy. We don't want to have to copy paste this line to every one of these functions. And this is where something called modifiers come into play. So we're going to go ahead and actually delete this line. And at the bottom, we're going to create our first modifier. A modifier is going to allow us to create a keyword that we can put right in the function declaration to add some functionality very quickly and easily to any function. To create a modifier, you use the modifier keyword, and then you set it up very similarly to a function. So our modifier is going to be called only owner. We don't give it a visibility like functions. And in here, we can put our code. So again, we'll say require the message.sender is equal to, not set to, is equal to the owner. And if it's not the owner, we're going to say sender is not owner, like this. And then underneath, we're going to put this little underscore with a semicolon. What we can do is we can take this only owner keyword and stick it in the function declaration of our withdraw. And what's going to happen now is it's going to execute what's in this modifier first. It's going to execute this require. And then this little underscore says, and then add whatever else you want to do in the function. So we're going to execute this require, then whatever else is in the function. And for our withdraw function, it's going to be everything else in here. In our modifier, if we had the underscore above the require, this means that we would execute the code inside the function first and then the require. So the order of your underscore matters. So now with this modifier keyword in the withdraw function, whenever you call the withdraw function, we first go, oh, there's a modifier. I got to drop down here. We'll execute this. Oh, here's an underscore. Time to go back to the function. Let's do what else is in the rest of the code. And then it'll come back down to the only order modifier and say, oh, is there anything else to do? Oh, there's nothing else. So I guess we're good. So let's see this all go through end to end. And remember, you don't actually have to deploy this to a testnet if you don't want to. But if you want to follow along, feel free to do so, of course, as well. To get started, let's, of course, compile fundme.sol. Looks good. Let's delete any contracts deployed previously. Let's make sure we're on injected provider MetaMask. And let's make sure that we are on a testnet. We are indeed. Let's make sure we have a little bit of testnet ETH in our wallet, and we sure do. And let's go down to the contract and make sure we're on the right contract. If you try to deploy something like an interface, you'll get an alert like this. This contract might be abstract, blah, blah, blah. So we're not going to do the interface. We're going to do the fundme contract, of course. We'll hit deploy. MetaMask will pop up. We'll go ahead and hit confirm on the MetaMask. And then we're going to have to wait a little bit for the contract to actually finish deploying. If we pull up the terminal, we can see the contract go through, and we can also see it in Remix here. Now we've got a number of buttons in here. We've got our red fund button, of course, which is because we have our fund function, which is payable. And this allows us to send ETH with this function. We have our withdraw function, which is just orange because it is not payable, although it is going to be withdrawing money out of the contract. And then we have our typical blue view and pure functions. The owner, of course, is going to be our MetaMask, since we are the ones who deployed this contract. Minimum USD is going to be 5. And these are, of course, going to be empty. We can call our fund function only if we send some value with it. If we try to call fund without any value, we're going to get this gas estimation error failed. And we'll even see didn't send enough ETH in the error log. So let's go ahead and cancel this. Again, we could send this, but that would be a huge waste of gas. So we'll cancel it. And let's get a value that's going to be enough. So I believe 0.01 ETH should be enough. Let's say 0.01 ETH. It looks like that's about $18. So back in Remix, let's do 0.01 ETH in terms of way, which is this value here. Paste that in. And we'll scroll down. Now, if we call fund, it does indeed go through. And we can go ahead and hit confirm on this as well. And we see that transaction pop up on Etherscan. And we might have to wait a little bit for this transaction to finish going through, finish indexing, etc. So let's give it a couple minutes. Oh, it looks like it's gone through. Fantastic. We can even see in the fundme contract, the balance has gone up to 0.01. And we can see if we look at funders at index 0, we can see our address. And if we copy our address and paste it into the mapping, address to amount funded, we do indeed see an amount in here. With this transaction fund being called, of course, on the testnet Etherscan, we can see all the data and information associated with this. And we can even scroll down and see the input data. We can see that this was calling the fund function. We'll learn more about the input data later. So now what we could do is we could do the reverse. We could go ahead and withdraw, and that should reset the mapping and the array back down to 0. For our modifier to work, we have to use withdraw on this account. If we switch to an account that isn't the owner of this contract, and we go ahead and reconnect, and we scroll down, we make sure value is 0, and we scroll down and try to hit withdraw, we'll see we get gas estimation failed, and we'll even say sender is not the owner. So we'll go ahead and cancel that. We'll switch back to account 1. We'll make sure we're working with account 1. Now we'll call withdraw. We'll see MetaMask does indeed pop up, and we can go ahead and confirm. And in just a minute, we'll see the balance reset. And if we call our funders and mapping, they should also have been reset. So let's wait a little bit. Now, if I try to call address to amount funded with that same address, we now get 0. And now if I look at funders at index 0, it actually errors and this isn't correct. Following are more advanced solidity constants. If you don't understand them the first time, don't let them stop you. They are not required to know to continue. The following is an excerpt from a slightly older edition of this course. You'll see that I don't use named imports like a noob, and a few other pieces of the code look slightly different. But this next section, we're going to go over a lot of really advanced solidity pieces here that are going to really advanced solidity fundamentals. These are going to be fantastic for saving gas, making your code look a lot cleaner, and just better coding practices overall. For those of you who are looking to go super far with this, definitely be sure to pay attention to this section because this will make you look like a badass when you code later on. Just remember, when we say JavaScript VM, we just mean Remix VM. Additionally, whenever we deploy to the Rinkeby testnet, just know that you should be deploying to the Sepolia testnet or whatever the most up-to-date testnet is. Or just don't deploy to the testnet and just follow along. We're going to modify this contract to make it a little bit more professional. It's not going to be end-to-end amazing, but it's going to be a little bit better, and you'll see why in a minute. So the first thing that we're going to do is we're going to look at some of these variables here. In particular, owner and minimum USD. Owner gets set one time in our contract here, and then it never changes again. Minimum USD gets set one time, even outside of the constructor. If we have variables that only get set one time, we can actually use some tools in Solidity to make them more gas efficient. For now, let's compile our FundMe contract and then deploy it to a JavaScript virtual machine. Remember, we can go ahead and deploy it right now. However, funding and withdrawing and doing any of the money stuff isn't going to work because again, we don't have a chain-link network on our JavaScript VM. So those aren't going to work so well. But for what we're going to do right now, we don't really care so much. Here's what we do care about. We do care about how much gas this costs to actually send. We do care about how much gas this costs to create. Right now, creating this contract costs about 859,000 gas. And we're going to add a couple of tricks right now to bring this number down. We're going to add some stuff back in a bit, which will bring it back up. But for now, we're going to learn some tricks to bring this number down. The two tricks that we're going to learn are the constant keyword and the immutable keyword. In their Solidity, there are two keywords that make it so that your variables can't be changed. And those keywords are constant and immutable. You can learn more about them in the Solidity documentation. If you assign a variable once outside of a function and then never change it, so if it's assigned at compile time, you can go ahead and add this constant keyword. We'll learn later about storage, but when you add a constant keyword, this minimum USD no longer takes up a storage spot and is much easier to read to. So now if we recompile this and we deploy this new contract, let's see if we saved any gas. If we look in the transaction logs now, we can grab the transaction cost of how much this cost to deploy. And let's compare it to how much it was before. Wow, we saved almost 19,000 gas. That's almost as much gas as it cost to send Ethereum. Typically, constant variables have a different naming convention. Typically, you'll want to do them all caps, like min, emum, underscore, USD. So all caps with underscores. So now let's just find minimum USD and replace that with all caps as well. With this interaction, we know that this variable is a constant variable and it's much cheaper to read from. Now, if we go ahead, compile this and redeploy in our FundMe contract, even though this is a view function, remember, view functions do have gas costs when called by a contract. As a constant variable, we can see the execution cost of this variable, 21,415 gas. So let's put a little note right underneath it. If we remove the constant variable, we delete this contract, we redeploy, we click FundMe, and we hit minimum USD again, we can now see how much gas this was cost if it wasn't a constant variable. We can see the gas cost did indeed go up. Now on chains that are much cheaper, this gas difference probably won't make it that much of a difference. But on more expensive chains like Ethereum, this is going to make a big difference. For example, on Ethereum, we can actually see current gas prices on Ethereum here. We can see that the current gas price of Ethereum is about 141 Gwei. So we'll go to our converter, Gwei to Wei, we'll copy the Wei price, times this, we'll get the gas price of calling our minimum USD, which is this number here, which if we put back in our Ethereum unit converter, we can see costs this much gas. And if we times that by the approximate current price of Ethereum, which is around $3,000, calling minimum USD as a constant is going to cost $9. Calling this at a non-constant is going to cost almost an entire dollar more. You can see how all these little gas optimization tricks are going to make your life a lot better. So let's keep this constant keyword in here. We'll learn more about constant and storage in later sections of this course. Now, as you're just getting started with this course and with Solidity, do not struggle and do not worry about making your contracts as gas efficient as possible. In the beginning, and especially right now, just write your contracts as best as you can. Once you get really good at gas, and once you get much later on in the course and much more advanced with Solidity, then you can start going back and working on gas optimizations. But do not let gas optimizations hold you back, or if you start stressing over it, just let it go. Don't worry about it and just write your code as best you can. So long story short, do not stress about gas optimizations right now. Now, another variable we only set one time is going to be our owner variable. Owner equals message.sender. We set this one time in the constructor. Variables that we set one time, but outside of the same line that they're declared, and we set them, for example, in the constructor, we can mark as immutable. Typically, a good convention for marking immutable variables is going to be doing I underscore, so that we know that these are immutable variables. They have very similar gas savings to the constant keyword. Owner, of course, is a variable that we can't set on the line here, because inside the global scope, there's no function going on. However, inside functions, because inside the global scope, there's going to be no message.sender. There's only going to be a message.sender when we're inside of a function. So inside here, we might say iOwner equals message.sender. And then, of course, we'll scroll down and we'll change this require only owner now equals iOwner. Now, if we compile that and deploy it, we can see how much gas calling iOwner is going to be with the immutableness. We get 21,508, which we'll go ahead and copy for now. And we'll put right here. We'll say immutable. Now, if we remove the immutable keyword, let's close this, redeploy. Now, if we scroll down to iOwner, scroll up the logs, we go down to the call, we scroll down, we see the execution cost was much more. So we'll do double backslash, paste that in here, gas for non-immutable. So you want to keep some of these tricks in mind when it comes to storing variables. The reason that these two save gas is because instead of storing these variables inside of a storage slot, we actually store them directly into the bytecode of the contract. And like I said, don't worry too much about that for now. Later on in the course, we'll teach you more about storage and a lot of this low-level stuff that comes with these contracts. But for now, just know that these exist and they're nice gas savers if you're only setting your variables once. All right, great. So we've just made our contract a little bit more gas efficient. Little gas efficiency improvements are going to be concepts I sprinkle throughout this course. And when we get to the more advanced section, I'm going to break down exactly what's going on and why all these gas efficiencies exist and what's going on behind the scenes for these gas efficiencies to occur. It's a little bit in the weeds, which is why I'm going to gloss over it right now. So if it's confusing, don't worry. I wouldn't let these gas efficiencies be the thing that slow you down. Awesome. So we have these two gas optimizations. How else can we make this contract a little bit more gas efficient? Well, one of the ways we can make this more gas efficient is by updating our requires. Right now, with our require statement, we actually have to store this sender is not an owner as a string array. Every single one of these characters in this error log needs to get stored individually. This string may not seem very big, but it's a lot bigger than the alternative with what we can do. As of 0.8.4 of Solidity, you can now actually do custom errors for our reverts. We declare them at the top and then use ifs instead of require, and then just add our revert statements. This ends up saving a lot of gas since we just call the error code as opposed to calling the entire string associated with the error. So for example, with our require down here, and with all of our requires, what we could do is instead of having this require, we could create a custom error. So at the top, what we could do is we could say error, not owner. And you'll notice that this is actually outside of the contract here. Now what we can do is we can take this error not owner, scroll down into our only owner. Instead of doing a require, we'll do an if statement. We'll say if message.sender is not owner. Then we're going to go ahead and revert with a not owner error. This ends up saving us a lot of gas since we don't have to store and emit this long string here. Now, in a lot of code today, you'll still see require a lot of places because these custom errors are pretty new in Solidity. So you'll want to get used to writing it both ways. I wouldn't be surprised if in the future, the syntax for some of these errors looks like this so that it's more readable. But for now, if you want to do a more gas efficient way than requires, you can use something like this. We could update all of our requires here for these custom errors, but for now, I'm going to leave both in just to show you the differences. This revert keyword does the exact same thing that require does without the conditional beforehand. So you can actually go ahead and revert any transaction or any function call in the middle of the function call. Now let's look at one more way to improve this contract. Sometimes people will try to interact with the contract that takes Ethereum or the native blockchain token without actually going through the required function calls that are needed. For example, on a JavaScript EVM here, I could actually try to send this contract money without calling the fund function. However, if I were to do that, what would happen? Would our fund function get triggered? No, it wouldn't get triggered. We wouldn't keep track of that funder. We wouldn't have that person's information updated in this contract. So if later on we want to give rewards or something, we wouldn't know about those funders. And this wouldn't be great because people would send our contract money without us ever knowing, and we wouldn't be able to give them any credit or anything. Additionally, maybe they called the wrong function by accident and they weren't using MetaMask and they weren't using a tool to tell them, hey, this transaction is likely going to fail. So what can we do in this case? What happens if someone sends this contract ETH without calling the fund function? Right now, if we were to send this fund me contract ETH, it would just go to the contract, right? And this contract just wouldn't keep track of those people. But there's actually a way for when people send money to this contract or people call a function that doesn't exist for us to still trigger some code. And now there are two special functions in Solidity. One is called receive and one is called the fallback. Now, in Solidity, there are actually a number of special functions, and two of these special functions are the receive special function and the fallback special function. A contract can have at most one receive function declared using the receive external payable without the function keyword. This function cannot have arguments, cannot return anything, and must have external visibility and a payable state mutability. What does that actually mean and or look like? Well, let's create a separate contract to go ahead and play with this. So in here, we're going to create a new file called fallbackexample.sol. And in here, we're going to add our basic pieces: SPX license identifier, MIT, pragma solidity, 0.8.7, and we'll do contract fallback example, like so. Feel free to pause the video to catch up to this point. Once we create our fallback contract, let's create a variable to go ahead and try to test this function. We'll create a uint256 public result variable. And let's create this receive function. So we'll say receive is going to be an external payable function. We don't add the function keyword for receive since Solidity knows that receive is a special function. Whenever we send Ethereum or make a transaction to this contract now, as long as there's no data associated with the transaction, this receive function will get triggered. What we can do in here now is we can say result equals 1. So let's go ahead and test this out on the JavaScript virtual machine. So we compile this. So we're going to go ahead and compile this. We'll go deploy it on the JavaScript virtual machine. We're going to deploy our fallback example, and we're going to see what result is initialized to. Since we haven't set anything for result, of course, is initialized to 0. But what if we were to send this contract some Ethereum? Well, receive would go ahead and be triggered here. We can actually send this contract some Ethereum directly by working with this low-level interactions bit here. Don't worry about what call data means for now. Just know that this area down here is a way we can send and work with different functions. And we can add parameters to this transaction by going up here and adjusting the variables up here. If we keep call data blank, it'll be the same as if we were in MetaMask and just hitting send and then choosing this contract address. Again, we can't actually use MetaMask since this is a virtual machine and not one of the networks that we're working with. So if I do, for example, I change this value to one way and I keep everything blank and I go ahead and hit this transaction button, which again, is going to be the same as hitting this send button, but only sending one way, what do you think will happen? Well, let's try it. We can see in the log area that we did indeed send a transaction. And if you look at the description here, you can even see it says from so-and-so to fallback example dot receive. It looks like it called our receive function, which should have updated our result to 1. So if we hit result now, we can indeed see that result has been updated to the value of 1. Well, let's go ahead and delete this. Let's deploy this contract again. And this time, let's have value be 0. Does receive get triggered this time? So let's pull this down. Let's hit transact. Let's leave the call data blank. We'll leave value at 0. So this will be the same as if we had sent 0 Ethereum to this contract. Let's hit transact. Looks like that went through. Do you think result is going to be 1 or 0? If you thought 1, you were correct. Our receive function gets triggered anytime we send a transaction to this contract now, and we don't specify a function and we keep the call data blank. When working with any other contract, like FundMe, for example, when we call one of these functions, we're actually just populating this call data bit with certain data that points to one of these functions up here. If we send a transaction and we add data to it, we could actually call one of these functions. Now let's try this again. Let's delete the contract again. We'll redeploy, open this up. Result is currently 0. Receive, like I said, only is triggered if our call data to it is blank. Now this time, if I add some call data to this transaction, do you think receive will be triggered this time? If we hit transact and remix, we actually get a pop-up saying fallback function is not defined. This is because whenever data is sent with a transaction, Solidity says, oh, well, since you're sending data, you're not looking for receive, you're looking for some function. So let me look for that function for you. I don't see any function that matches the 0x00. So I'm going to look for your fallback function. Remix is smart enough to know that we don't have a fallback function. The second special function in Solidity is called the fallback function. This is very similar to the receive function, except for the fact that it can work even when data is sent along with transaction. So our fallback will look something like this. Fallback, external, payable, result equals 2. Fallback is another one of these functions where we're not going to put the function selector because Solidity is expecting this. Actually, you're already familiar with one other special function. If we go back to our FundMe, our constructor, for example, is another type of special function. There's no function keyword. Solidity knows that this constructor is immediately called when we deploy this contract. So now we have our fallback function. Let's go ahead and compile this. Let's delete our old contract. Let's go ahead and deploy this new contract. Let's click here. We hit result. We do indeed see it's set to 0. Now, if I add this 0x00 and I send this and I hit transact, this is equivalent to calling our contract here without a valid function. So our contract goes, I don't recognize what you're trying to tell me here. I'm going to refer you to our fallback. And now if we hit result, we see that it's been updated to 2. If we take this away, Solidity will go, it looks like you're trying to send some Ethereum or call this contract without specifying what you want to do. Well, I have a receive function, so I'm just going to go ahead and forward you to that. So if we call transact, we hit result, we see it updates back to 1. Add some data, hit transact, we see it updates to 2. No data, updates to 1. SolidityByExample.org has a wonderful little chart that we can use to figure out whether or not receive is going to get triggered or fallback is going to get triggered. If it is empty and there's a receive function, it'll call the receive function. If it is data and there's no receive function, it'll just go to the fallback function. And if there's no fallback function, it might error out. So this is a lot of really fantastic information here. How can we apply this to our FundMe contract here? Well, what we can do now in our FundMe is we can add these fallback and receive functions just in case somebody actually sends us contract money instead of calling the fund function correctly. So what we can do is let's add a receive function. So if somebody accidentally sends it money, we can still process the transaction. We'll say receive is going to be external, payable, And we'll just have the receive function call fund. And we'll do the same thing with our fallback function. We'll have fallback external payable. We'll just have it automatically call fund. Now, if somebody accidentally sends us money without calling our fund function, it'll still automatically route them over to the fund function. This means too that if somebody doesn't send us enough funding, that transaction will still get reverted. So let's go ahead now and let's switch to RinkB to test this on a real testnet. I'm on RinkB in my MetaMask. Let's switch over to Injected Web3. And we'll scroll down. We'll choose our FundMe contract. And we'll go ahead and deploy this. MetaMask pops up. I'm going to go ahead and confirm the transaction. And we see our FundMe contract here. Right now, we can see I'm the owner. We can see minimum USD. And we can see, of course, that it's a blank contract and there's nothing funded in here. If we copy the address and then go to RinkB Etherscan, paste the address in, we can see that there's no Ether in here. And the only transaction associated with this has been the contract creation. We saw what happened before when we hit the fund function. Our contract was updated with a new balance, and that funder was added to our array. Let's see what happens now if we just directly send this contract money without calling the fund function here. If we did this right, our receive function should pick it up and kick the transaction over to fund. So let's copy this address. We'll go to our MetaMask. We'll hit send, paste the address in here. We'll do 0.02 ETH again, because this should be more than the minimum amount in USD. We'll hit next. I'll go ahead and confirm this. And after a slight delay, if we did this right, we should see this transaction having called the fund function here. Now that our transaction has gone through, and after a brief delay and waiting for Etherscan to update, we do indeed see that our balance has updated to 0.02, which of course, this makes sense. And we see in the transactions list here, we see that this actually went through as a transfer instead of us calling the fund function. Let's go ahead and remix and see if our funders was updated. It looks like it was. At the 0th position of funders, we have our address. And if we take our address and pop it into address to amount funded, we can see exactly how much we had funded. This means that since we added this receive function in here, we automatically had to call our fund function up here. So awesome work. We were able to add a receive function to help people who accidentally call the wrong function or accidentally send this contract money instead of correctly calling the fund function. Now, if they had directly called the fund function, it would have cost them a little bit less gas, but at least this time they're going to get credit and added to our funders array for having sent our funding contract money. We've even learned some advanced sections of Solidity. And this is going to be the last time that we start our projects in Remix. We're going to be moving over to a code editor now where we can get even more advanced with our Solidity and our setups. For the most part, you've gone over the vast majority of Solidity basics. There are a number of things that we still haven't learned yet. And the reason we haven't gone into them is because they get more advanced and understanding their real use doesn't really make too much sense until a little bit later. Some of the things that we're going to go over are enums, events, try-catch, function selectors, ABI encoding, hashing, and then YUL/assembly. However, if you've gotten this far, you probably can read most Solidity code and understand what's going on, which is absolutely fantastic. So you should give yourself a huge round of applause for getting this far and doing this. Let's do a quick summary of this more advanced section and make sure we understand what we learned. In Solidity, there are a couple special functions. Some of them are receive, fallback, and constructor. These functions don't need to have the function keyword and instead can just be called like so. Receive and fallback are two very special functions. If data is sent with a transaction and no function was specified, the transaction will default to the fallback function if that fallback function exists. If data is empty and there's a receive function, it'll call the receive function. There are a couple of keywords that can help us save gas in the long run. Some of those keywords are going to be constant and immutable. Constant and immutable are for variables that can only be declared and updated once. Once we say minimum USD is 50 times 1E18, this minimum USD can never be changed again. And this helps us save gas. Immutable can also save gas similar to constant, However, immutable variables can be declared one time in the constructor. Once an immutable variable is declared, it can't be changed later on. In fact, if we even tried to update an immutable variable or a constant variable, and we compiled, our compiler would give us an error saying, can't write to immutable here. Or if we tried to change a constant variable, our compiler would say, hey, you can't assign to a constant variable. Sorry. In Remix, if we want to send Ether to a contract that's on the JavaScript virtual machine, we can deploy that contract, and then in the contract, we can just hit the transact button without any call data and update the value that we send with the transaction. If call data is blank, it'll trigger a receive function if it exists, but if there's data that doesn't specify any of the other functions, it'll trigger the fallback function. All right, my code's done. Time to ship it.
Delivery free, box due, dog water, 0 earned, 0 PR.
In the age of AI, debugging and getting into software engineering has never been easier. Here are the exact 6 steps you need to take to unblock yourself from any software engineering error you'll ever get. Number 1, tinker. Try to pinpoint your error. You can usually use an AI buddy to help you out here. Pinpointing your error will potentially solve your problem before even going to an AI and allow you to craft a better question to an AI. Once you've pinpointed the issue, you can move to step 2, which is ask your AI. You can use ChatGPT, Find, Bing's AI, or if you want to give wrong answers, Google's Bard. There's 6 principles to prompt engineering so that you can get the best out of your AI. Write clear and specific instructions, give as much context as possible, use delimiters to clearly indicate distinct parts of the input, and especially look out for something called hallucinations. Hallucinations are when your AI gives you an output that it thinks is right but is completely wrong. For example, if I write about writing solidity invariant tests in Foundry, GPT disgraces us by saying we have to npm install it from OpenZeppelin. These can be tough to spot, but once you try it out, you'll see it doesn't work. And finally, you want to understand the limitations of the AI you're working with and iterate constantly. Large language language models are trained on human conversation, so you can interact with them as if you're having a conversation. But it's important to know the limitations of these AIs, as most AIs have a limit on how many tokens or words they can keep in context at one time. AI is trained off human language, so if you're good at asking other humans questions, you'll probably be good at asking robots questions too. Asking questions is a skill, so keep practicing. I've got a link in the description to learn.deeplearning.ai, which is a free course to help software engineers be better prompt engineers. Now, when the AIs can't help you, you'll have to go back to the old standbys, actually doing work yourself. And one of the first pieces of work is reading the documentation. You probably should have done this already. However, we can still use ChatGPT because a strategy that I constantly use is I'll copy paste sections of the documentation, add ChatGPT as context, and say something like the above are the docs for tool X. Based on those docs, how do I do Y? So Google might be crying because ChatGPT is eating its lunch, but Google still has what AI doesn't have, the entire internet. Previously, anytime I ran into an issue, I prayed someone else had run into it before I made a post on it so I could Google search that exact issue. There's a new tool called Find that combines web search with AI, as it does a web search and it crawls through all the data of the sites, reads them all, and then gives you an answer based off of what it reads. 5, ask in a forum. Sometimes the information just isn't out there, and we need to ask human beings. We always want to ask our question on a webbed indexed forum like Stack Exchange, Stack Overflow, Piranha, or Reddit. This way, web crawlers and more likely AIs can scrape the data from these sites and learn from us. That way, the next time we have this question, we can get our answers quickly. Asking on Discord and Twitter are because your knowledge will get lost to the unsearchable hellhole of conversations that Discord is. And web crawlers don't index them. The super secret alpha is to ask a question on Stack Exchange and then post your Stack Exchange link to Discord. You should 100% always ask your questions and format them with Markdown. And if you're not sure how to do Markdown, you can ask ChatGPT to help you format your questions in Markdown. Ask on the support GitHub or forum. Is the tool you're working on open source? Awesome. Ask a well-formatted question on their Git page. Not open source?
Never use that tool again.
This is how we improve our tools, by creating issues, engaging with each other, and even taking on issues and contributing to the open source code. And then finally, iterate. Do all these same steps over again. And as always, keep hopping through the code, and until next time, stay riveting, my fellow blockchaineers. All right, fantastic. So now we know a little bit more about the different tools and techniques we can use when we do, in fact, get stuck. We can use something like ChatGPT, forums to ask questions. We obviously want to Google search. And especially for this course, you definitely want to make sure you use the discussions channel but I wanted to give you some very specific tips about working with this course. Number one, limit your self-triaging to 15 or 20 minutes. For example, if we're trying to compile our price converter.sol and maybe we forgot to add the address in here, right? And we're going to go ahead and compile and we're getting this error. This is exactly one argument expected for explicit type conversion. Now, this should be pretty obvious what the error is. Hey, it's expecting one argument, and we obviously just removed that argument, but maybe you're having a really hard time and you're trying all this different stuff and you can't seem to figure it out. Limit yourself to 15 or 20 minutes. We do not want to be messing around for so long that we can't figure something out, right? Something like this would be very easy for us to compile, copy this error, go to ChatGPT and say something like, hey, I'm getting an error compiling my Solidity. Here is the error. Do 3 backticks, paste it in here like that. 3 backticks is markdown. And like we said in the video, we want to use delimiters to clearly identify what is code versus what is not. Oops, and I hit enter. Whoops, the daisy. We're actually going to hit stop generating and we're going to copy paste the question again. Now we're going to say, here is my Solidity. It's wrong. And then we'll copy the Solidity line. Once again, 3 backticks. We'll say Solidity here. We'll paste it in. 3 backticks to end it. Hit enter. And it'll probably give us the answer here. And sure enough, the error message suggests that you need to provide an address when using explicit type conversion. So we go, okay, whoops, we need to actually add an address in here. It gives us an example. And we can go back to our code and paste that address in here and be good to go. So limit self-triage to 15, 20 minutes. That's going to be the first tip. Number 2, don't be afraid to ask AI, but don't skip learning. The purpose of this course is for you to be able to learn everything here. AI is going to get things wrong. And it's only the people who actually have learned what's going on under the hood who are going to be able to call out when AI gets something wrong. When AI gets something wrong, it does something called hallucinate. And we talked a little bit about that in that AI video we just watched. So hallucinations are when the AI makes something up that it thinks is right, but it's completely wrong. And that's something we absolutely need to watch out for when we're coding and when we're learning. A perfect example of this is with Foundry, which is a tool we're about to learn very soon. In order for us to install Foundry, we actually need to run this command, right? Get foundry.sh. It's the first thing that it tells us to do. At the time of recording, ChatGPT has not been trained on the Foundry tool. So if I ask it a question like, I'd like to initialize a Foundry project with Solidity, can you show me how to do that? And we'll hit enter. So the first sentence out the gate is wrong. It's not aware of Foundry, so it tried to guess what Foundry was and it got it wrong. It is not a Rust-based framework for building blockchains at all, and it is directly related to Solidity. So it's really important that we use AI to augment our learning, but we don't skip over the learning with AI. It's really good to bounce questions, good ideas off of, but in order for us to be even able to recognize when Foundry is hallucinating and making stuff up, we need to have that knowledge ourselves. Step 3, of course, use the forums. Web3education.dev will have a place for you to ask questions. But in the meantime, definitely be sure to use the Foundry full course discussions. Use this to your advantage. And use this to help other people out who have questions. This is a community project. We're all going to be helping each other out learning. Number 3, Google the exact error. If AI doesn't know, the forums aren't know, Google the exact error. Maybe somebody else has come across this error previously, ask the question online, and you can just Google it. And then, of course, post your question in Stack Exchange or Piranha. And like we said in that AI video, you want to use Markdown and format your questions as best as possible. So if you're unfamiliar with how to use Markdown, if you're unfamiliar with how to format your questions, again, please be sure to ask ChatGPT or some other AI how to best format your question. You can even simply say, ask ChatGPT, could you give me an example of a well-formatted Stack Overflow question with code? And it'll actually give us a really good formatted question. So it gives us the question, it formats the code for us. It's using this with the 3 backticks that I showed you in order to get this code block here. It's using 3 backticks, and it's being very verbose in giving all the details of the question. So be sure to ask questions like ChatGPT. Awesome. Again, let's say we're in here, we compile, we get this error, exactly one argument expected for explicit type conversion. If we copy this error, go to Google, We paste just the error in. We'll remove this, our specific code. Looks like the first thing we get in Google is actually contract inheritance. And we can see that this is actually exactly the error that we're getting. It looks like this does actually explain the answer, but it's a little bit confusing to understand here. So maybe you would copy paste this into ChatGPT as context, right? There's a lot of creative ways you can approach debugging some of your issues. Obviously, when you're out in the wild and you're actually building things yourself, obviously the education site and the discussions channel of the GitHub repo, the people in these aren't going to have context for the new creative thing that you're working on. So I want you to get used to doing that methodology that we're teaching here, right? Asking your AI buddy, if your AI buddy doesn't know, Googling, asking questions on Stack Exchange Ethereum, asking questions on Piranha. Piranha is arguably better because you're asking your questions in a decentralized location as opposed to a centralized server. But I definitely want you to practice asking questions and go to Piranha, go to Stack Exchange, make accounts for these so that when you do run into an issue, because you will, you'll know where to post them. I highly encourage you to pause and post a question on one of these forums right now, just so that you get used to it, just so that you get out of your shell. And you're going to suck at asking questions in the beginning, and that's okay. You will get better at asking questions as you continue with this course. Asking good questions is a skill in itself. And if you learn how to ask very good questions, that's the secret sauce to being amazing at AI prompting as well. Now, the final step in all of this is actually going to be posting an issue on GitHub/Git. A surprisingly incredibly important part of being a software engineer and being a developer in Web3 is interacting with the community. The vast majority of these tools that we're working with are going to be something called open source, meaning that the code associated with them is actually available for anybody to view. This tool Foundry that we're going to be working with is one such example. And if you see, it has this issues tab where there's just a ton of issues people are posting while using this tool. This is how code is able to be improved and move forward. All this code is public for people to use and work with. And if there's a question that isn't answered, you can post here and tell the developers of this tool, hey, I'm running into an issue. Maybe we should make a project improvement. I would say be very respectful with the way that you make issues. You definitely want to do some searching on issues to make sure that nobody else has asked the question that you're working with. And be sure to use these other resources first, like Piranha, like Stack Exchange. But in the future, once you leave this course, it's going to be incredibly important for you to participate in the ecosystem by making issues, by making pull requests, and actually improving some of the tools that we're going to be working with yourself. Even Ethereum has a GitHub, and if there's any improvements that you want to make, you can add an EIP to actually improve Ethereum. We'll talk about EIPs some more later. You can improve some of the clients that Ethereum runs. So interacting with each other is incredibly important. And in fact, if you don't have a GitHub, we are going to get you set up with GitHub right now, because GitHub is the platform that most developers use to share code and write code and interact with code in between each other. So if you don't have a GitHub, let's sign up right now. And we're going to use the GitHub to create our own portfolios of all the different cool coding projects that we've created. This way, when you go to apply for a job, you can say, hey, go look at my GitHub. I've got all these really cool projects. So we're going to make you a GitHub right now. If you don't have an email, you're going to need an email. I made a burner account just for this video. And I'm also going to walk you through formatting a question. And I know I'm belaboring the point here, but I really, really want to stress the importance of formatting these questions really well. So we're actually going to show a clip from my past video. So we're going to be using the full blockchain utility course JS. But again, for this video, just be sure to use the GitHub repo associated with this course and not that other old GitHub repo. All right, let's watch this video. In fact, if you haven't already, let's sign up for GitHub right now and let me walk you through formatting one of these questions. Because the better you format your questions, the better chance you have of actually getting the answer. And remember, when asking questions on these forums, when asking questions in these discussion communities, people answer these questions out of the goodness of their heart, right? So if you don't get a response, there's a chance that maybe nobody knows, maybe your question isn't formatted very well, and etc. So we're going to learn how to ask really good questions here. And if you're new to blockchain, do not skip this section, okay? This is going to be that piece that's going to give you the superpower to unblock yourself from any coding issue you run into. So don't skip this part. Be sure to follow along. Okay, so if you don't have a GitHub already, you do need an email to get started. So I'm going to go ahead and sign in. I made a burner account just for this video. So what we're going to do, we're going to go ahead and sign up. GitHub, enter your email. and we hit create account. They're going to send us an email. So we're going to come back to our email. We're going to get our launch code here, paste it in, answer a little bit of information. We're going to choose the free version. And fantastic, we've now created a GitHub profile. Awesome, so now we've created a GitHub. So I'm actually using a GitHub that I used in my last course, so that's why I have all these repositories over here. Now, in order to create a new discussion over the Foundry Full Course F23, let's go over to the Discussions tab. We'll hit New Discussion, and we'll hit General, and I'll say something like Test Discussion. Be like, feel free to say hello here. Start discussion. Now I'm going to show you a question that's formatted poorly, and I want you to never, ever, ever ask a question like this. And if you see somebody ask a question like this, please help them format their question correctly. Hey, why my code not be good? And then let's just have it be the issue like this, right? What's wrong with this? Okay, well, why my code not be good obviously isn't clear what's going on. The code isn't formatted well, and even an AI would have a hard time answering this. So let's fix this to be a little bit better. As we know, we want to copy the exact error we're getting. So we'll copy the error, we'll go back, we'll say, I am receiving this error. We'll do the 3 little backticks, paste our error right in here, like that. Actually, let's be even more explicit. I'm receiving this error while compiling. Here's my code, 3 backticks. We'll put solidity here. We'll copy the whole line that is erroring, paste it in here. Can someone help me figure out what the issue is? Right, and you see how this is much, much better, right? We have these 2 blocks that pop up because we did the backticks. And the secret is that this is going to get you a much better answer from an AI as well, right? If we edit this, we can copy the whole thing in Markdown, go over to ChatGPT, paste it in, zoom out a little bit, and we're going to get actually an answer. Hey, you're receiving this error because you're trying to create an instance of aggregator v interface without providing the necessary argument, blah, blah, blah. Oh, and it actually gives an updated version of that, but it helps us out here. So format your questions correctly. You will get better answers from both AIs and humans. And I know I'm spending a long time on this, but I really, really need you to understand that the secret to prompt engineering is actually just being able to ask better formatted questions with human beings. And it's better for interacting with human beings as well. Now, the other thing that I did really well here was I only posted the relevant code to the error that I was getting. What we see a lot of people do is they just copy paste their entire code base into here. This is not very helpful, as it's going to make somebody who wants to help you their job a lot harder. If they have to read your entire code base, right? If we reply here, this is so much more reading for them to do. It's going to take them a lot longer, and they might not actually read it. And we didn't actually highlight this with the backticks. And it goes the same thing with AI. If you give your AI too much text, it can't read all of the text because, again, some of these AIs have limitations in how much text they can read. So it's the exact same thing with working with human beings. So feel free to take some time to either in ChatGPT or whatever AI you're using, or in this test discussion forum to post some well-formatted questions. And remember, you can use AI to help you get those formatted questions in Markdown. Be sure to ask ChatGPT to give you the output in Markdown. So if you haven't worked with Markdown before, that's okay. You'll learn as you go along. But one of the biggest differences, especially when working with Markdown, that's going to make your code so much more readable, and I 100% need you to always do this whenever you ask questions, is you see how this got like some syntax highlighting in this above question? Well, if we go click edit again, we can actually see why. Up here, we did those 3 backticks, and then we typed the word solidity. When you do these 3 backticks in your questions, if you type the word or you type the language next to the first 3 backticks, it'll actually add some formatting to make it more readable. So if we scroll down to this poorly formatted question, you can see that this is just all white and like impossible to read. It would be at least slightly better if we hit edit, and next to these 3 backticks, we wrote solidity. If this was like Java code or Python code, we could write Python or Java or whatever, but since this is solidity, we'll write solidity. I'll hit update, and you can see that it is substantially nicer and it is much more readable now. So even though this is still a bad question, obviously, because we just copy pasted all of our code, it's at least much more readable. So anytime you do a code block like this of any of your code, absolutely 100% be sure to do the 3 backticks, and then the language of the block of code. So just remember this. There are no bad questions, but there are poorly formatted questions. Make your questions well formatted for both human beings and for AI. And then most importantly, be sure to join these forums. And like I've said 100 times, interact with these people, interact and help and give back. The more people that use and are good at the tool that you're working with, the more likely that they're going to help you sometime in the future. And this is how I've met so many people in the industry, is just giving back and interacting with other people. So whenever you ask a question, especially in the beginning, because in the beginning, you're going to have more questions than not, be sure to at least try to go back and answer a question. Think of it as question and answer debt. Every time you answer a question, make a little mental note and say, in the future, I need to at least try to answer one of somebody else's questions. This is how we grow and move so much faster. Now, this next piece that I'm going to show you is actually outside of this course, but it's a resource that I wanted to show you in case after this course is done, you want more resources to learn about Ethereum and learn about the EVM. It's with my good friend Austin, who's going to show you Speedrun Ethereum, and definitely something you might want to check out after taking this course.
What's up? I'm Austin Griffith. Happy Bowtie Friday. I want to show you the best way to get started building on Ethereum. It's speedrunethereum.com. It'll teach you how and why. You'll build a simple NFT. You'll build a decentralized staking app. You'll learn that the superpower of Ethereum is allowing you, the builder, to create a simple set of rules where an adversarial group of people can coordinate financially. You'll build a token vendor. You'll build a dice game, and you'll learn about randomness on chain and where it works and where it doesn't and what you can do about that. You'll learn about a DEX and what a hyperstructure is and how people can use liquidity to swap. You'll learn about state channel and scalability and signed messages and multi-sig wallets and account abstraction and SVG NFTs. Lots of fun stuff along the way. Like I said, not just the how, but the why. Go to speedrunethereum.com and get started today. It'll have you do a quick video, and then it says to use Scaffold ETH to start tinkering. I want to show you how to do that. First of all this stuff is open source. It's all ungated and open source. Just get in and get learning, okay? But this Scaffold ETH thing, Scaffold ETH is a great way to tinker with Solidity and kind of get your bearings, right? So let me show Scaffold ETH too, just for a second. If we zoom in, I've already kind of gone through the whole README and installed everything. I want to show this right here. Here's a smart contract, and I have my front end that's auto adapting to the smart contract. And so when in Speedrun Ethereum, it tells you to tinker with each one of these concepts. Let's just go look at mappings or structs or modifiers. Let's just go look at a mapping, and let's grab a mapping, right? And let's copy and paste it right into our smart contract. So something called my map, I don't even know what it is, right? And then we yarn deploy, and we'll see that my map show up over here. And this is kind of the feedback loop I want you to get into, where you can grab some stuff from Solidity by example, paste it into your smart contract, deploy it locally, and then tinker with it. There's my map. Let's see what Vitalik's balance is in my map. It's 0. Oh, okay, so check out Speedrun Ethereum, check out Scaffold ETH, get started building cool things on Ethereum today.